Welcome, Samuel.
Hey,
Thank you so much for joining me and chatting about TensorMesh and Valkey today. So to begin with, tell us a little bit about TensorMesh and LMCache.
yeah, so LMCache is an open source project, currently the largest for KV cache management for LLMs. And what we basically do is utilize all of the resources on your physical machines, DRAM, as well as SSD, as well as allow you to connect your LLMs to remote databases to increase their capacity to hold a type of data called KV cache, which is the intermediate states that are computed by the LLM on your context.
Awesome. So let's start to talk a little bit about performance in LMCache and KV cache in general. One of the things I learned today is we focus a lot on tail latency and not so much on general latencies across the board. So why is that?
So this is specific to how the transformer computes. So unlike perhaps video generation, where if you receive some data, you can render a blurrier image or render a few frames first. For KV cache, you need to receive all of your KV cache for all of your tokens before the LLM can start to generate the next token. So what this causes is that when you're optimizing for a server-client relationship, you need to optimize for P99 latency because every single chunk needs to arrive. So the last chunk will be dragging your entire inference down.
Awesome. And then let's continue to talk about some of the specific optimizations that you did in order to improve performance. You mentioned this idea of chunks and chunking. What does that mean?
Great question. So obviously, when we talk to LLMs, we can give it a variable size piece of text. And what that translates to is a variable size number of tokens. But we can't store variable size objects arbitrarily into object stores. So we need to split them into fixed size chunks. Normally, we split it along the token dimension for 256 tokens per object.
Got it. And what does that do to performance then?
So chunking for KV cache is a specific invariant that we can take advantage of for throughput optimization because as expected, you can't perfectly divide your context length into the fixed chunk size that you set beforehand. So you're going to have this little tail at the end, which is the remainder that is less than your chunk size. And if we do a little trick where we decide not to store this very last chunk, then we get the invariant that every single object that we store, read and write, is the exact same size. So then we no longer have to store any metadata for these objects regarding their size. And also when we parse the byte stream coming back, during a read, we can actually not have to check for the delimiter in the REST protocol throughout the entire parsing of the byte stream. And so when we implemented this specific optimization for KV cache, we saw a 2 times improvement from 2 gigabytes per second to around 4 to 5 gigabytes per second.
Nice. I guess that math works out, huh?
It
If you
does.
don't have to read the metadata about how much you need to read before you delimit, then you can kind of just blindly always read the fixed size because you know beforehand already what the sizes are.
Exactly.
Yeah. It's also pretty specific to this workflow. You can't apply this generally as a solution, but it's perfect for if you know that you're going to be using LM cache or this for KV cache purposes,
Right.
like chunking.
If you have the guarantee that all of your data is going to be the exact same size.
Yeah. And then let's move on then to talk about the next part of the optimization that pushes us past 4 gigabytes per second. This idea of Python global interpreter lock and removing that from the critical path as much as possible. So talk to me a little bit more about that process and sort of how to optimize that part.
Yeah, so to give a tiny bit of context first, so the LLM ecosystem, the ML ecosystem in general is mostly built in Python. For example, PyTorch, the inference engines like VLM, SGLang, and LMCache, that was also a reason for building in Python. But Python is not the most performant language. It has something called a global interpreter lock where 2 threads cannot truly concurrently run on 2 cores. So we noticed this during profiling where even though storing and retrieving KV cache is an IO-bound workload, the global interpreter lock would serialize the completions of each of your reads and writes. And furthermore, if you submit multiple coroutines to Python's event loop at once, you actually don't know when Python will schedule these because it's only able to run one coroutine at once. So it runs one coroutine and it might go do some other work in the inference engine, and then that creates gaps inside of your reads and writes.
Got it. So how do we get around this?
Yeah, so the only way really is to lower ourselves into a more performant language like C++ or Rust. And so we chose C++ specifically, but obviously we still have to do some pi binding at the end to wrap it back up to Python.
Got it. So then how does the Python part of the interface hand off then to C++?
Really good question. So the Python interface needs to have as minimal of a scheduling boundary with the C++ as possible. So as mentioned earlier, because KV cache has this property where all of your objects need to arrive before the inference for this request can begin, we can, from the Python side, safely have only batched operations. So for a given request, we say from the Python side, this is one request, one batched get operation, and then the C++ side is responsible for splitting up that one batched operation into multiple threads to do reads and writes into all of the fixed size chunks.
Interesting. And again, it's because you have this prior knowledge that the entire thing needs to get processed as one big batch rather than individual requests.
This prior knowledge isn't completely free lunch, so the last little tail does have to be recomputed, but that's worth the cost of the much faster throughput.
Yeah, that's true because you had to drop it for the chunking. Oh, right. And then we also talked a little bit more about this idea of using a async submission and sort of an interrupt process. So tell us a little bit more about that.
Yeah, so the inspiration for this is from some pretty traditional libraries. In Linux, for example, IOUring. And this is a system where instead of using the POSIX interface to read and write, where every time you call read and write, the kernel takes over from your user space, you're able to put multiple jobs into a user ring. That's why it's called IOUring. And the kernel will take all these jobs, complete them, and then give you a completion queue to tell you when it's done. So we have a very similar system where the Python side asynchronously puts tasks, batched gets, and retrieves into a submission queue. And then we use a Linux interface called eventfd, which looks like a file descriptor, but it allows the C++ side to write to this file. And the Python side is woken up by the kernel as pretty much like a file completion.
Yeah, that's pretty interesting. When I was talking to you about this at first, I myself, in previous talks and previous work, have sort of run into similar dimensions of this with network interrupts. So in TCP network transfers, we have this idea of batching and pipelining requests and packets together so that they arrive at the kernel, at the socket, around the same time so that one socket read is sort of amortized, that cost, you can read a bunch of packets together. And then this other idea of having a CPU interrupt for the CPU to pick up the work and do the compute, you want to balance between how often you interrupt the CPU and like how many packets you've accumulated. But if you wait too long, then some of the earlier packets now have higher latency. So it's a really interesting problem space where there isn't necessarily one right answer. You kind of have to benchmark a whole bunch to tune it for a particular workload.
Definitely. And I don't think we reinvented the wheel or anything here. As you said, these are some pretty standard systems level optimizations.
Yeah, for sure. Okay, so to end us off, I'd like to understand what else we could be doing here. I'm sure this is just the tip of the iceberg in terms of optimizations.
Yeah, great question. So one thing that we like to call LMCache is it's the socket for LLMs. All of the clients that we have to connect to databases to store KV cache are only client side. So all of the optimizations we did, zero copy, fixed size workloads, removing the global interpreter lock, all of these are from the Valkey client side. So surely there's a lot of work and potential room for optimization on the Valkey server side as well.
Yeah.
And I think that the Valkey ecosystem is working really hard on that. We saw some PRs for large copy, for example.
Yeah, for sure. Actually, some of the things we've already talked about that's been implemented on the client side has either been already merged or in the middle of being coded up, like zero copy, reducing the number of mem copies on the server threading side, as well as IO threads in Valkey 9 to sort of help retrieve these large objects off of DRAM or disk in the future. So this data tiering idea, and also just in general, working with larger objects is kind of an unusual use case in the traditional caching sense, where you see a lot of tinier objects being accessed very frequently. So this is kind of the opposite of that, where you have larger objects being accessed at lower TPS. So some of the optimizations on the server side in Valkey 9 is actually specifically for large objects and aimed at improving tail latency. So we're excited to kind of see everything come together and for the throughput numbers to keep going up. Well, thank you so much for sitting down with me. Looking
right.
forward to next time.
Really grateful to be here. Thanks.